All right, so welcome everyone, and I'm going to give a very brief introduction for the workshop about scientific machine learning and the plans for going forward. So the basic idea is here, all right? This is an example of how to use a neural network to predict two-dimensional flow around the cylinder. So the basic idea is, I'm sorry, I'm trying to put this on, should I put this on a loop? Let's go back. So here, what you're seeing is the solution of Navier-Stokes equations with the advection of a tracer. So this tracer is some kind of contrast or food coloring that you can put in the water to that can be measured. Everything else cannot be measured. So you know, the velocity, the pressure, and also you do not know the geometry. So the only thing you have is the data from the tracer and the Navier-Stokes equations. So with only this information, then you can use a neural network to predict all four fields without any boundary conditions or geometry. So a traditional numerical method would need, of course, all the boundary conditions and the geometry of the cylinder in order to solve this at a high cost. But here, so this opens up a new realm of possibilities where, for instance, when you're measuring the flow in arteries in the body, the blood flow, you do not know the boundary conditions or the geometry, but you can measure the contrast. You can inject a tracer in the body, and you can measure that. So then you can calculate the pressure on the artery walls, for instance, if you have an aneurysm or something. So this is actually in a paper by another group, but we coded this independently on TensorFlow. And we have this demo also on our SciML website. So this is to give an idea. So basically, the scientific machine learning is still machine learning. It's not something different. You still have an input and an output, a target that you're trying to predict. I mean, so you train your algorithm to learn this input-output map. So at the input, you have space, time, frequency, angle, whatever the physical variables are. And at the target that you're trying to predict, you're trying to predict the experimental data or sensor data. And also, of course, agree with any boundary conditions, initial conditions. So this is the data of the problem. And you're trying to learn this input-output map. And of course, in the case of neural networks, we know that this is a universal approximator. So, you are able to approximate any continuous map from input to output, given enough data. So the difference now with respect to traditional machine learning is that we have physical laws. And by physical laws, I also mean chemistry, biology. Okay, so we have scientific laws. And the basic idea is this will constrain the algorithm. So that's why you may solve this problem, in fact, without any experimental data. So just like as a numerical solver, traditional numerical solver, or you can solve this problem with data, but no, like I said again, no boundary conditions or initial conditions. So this is different from the traditional machine learning, but it still have forward and inverse modeling. You can estimate parameters. You can recover hidden latent variables, just like machine learning. And And then the principle for neural networks, at least, is these neural networks is not the only class of algorithms that are used in scientific machine learning. You can also use other algorithms like kernel methods, Gaussian processes, for instance. But the most popular method now used in scientific machine learning is the physics-informed neural network. So for the physics-informed neural network, you're going to train a network using, like I said, points, data points scattered across the domain. So in the lower left, you can see a domain, space-time domain, and you can see several classes of points. You have initial condition points, boundary points, sensor data, and then you also have collocation points, which is where you enforce the PDE. So you have a PDE, let's say Navier-Stokes equations. This is going to be enforced in the at the collocation points. So essentially, the loss function of the neural network that you're trying to minimize will enforce agreement with the initial condition, with the boundary points, the sensor data, and the collocation points. So basically, that's the idea of just going to train a neural network as you usually do. Okay. Now, the good news is that you have unlimited data for the initial condition and residue and boundary points, not sensor data. But for the other points, it's like you have unlimited data. But like I said, in some cases, you do not know some of these conditions. Okay, so switching to, Gian, let me know when I'm running out of time, okay? Because I don't have my watch. Well, so essentially, okay. So essentially, the scientific machine learning, Nick already gave outstanding presentation, but just let me add that we have 9 faculty members. We have from all across the university. We also have 2 postdocs, Ming Zhang and Dehao Lu. And we also have support for graduate students, for undergraduate students, for community building events. And please take a look at our website to get more information. We have 3 pilot projects. They are all represented today during the workshop. So this is the materials research project, microstructure, phase field model project. We have the oil reservoir simulation project, and we have the supernovae project. All of these projects are represented here today during the workshop, so you're going to hear about them. These are the core projects. We are looking to expand with more projects in the future. We have events, so we have workshops like this one. We have training workshops on using SciML software. Levi, my PhD student, this is his picture here. He teaches a workshop on using TensorDiffQ, which is a TensorFlow-based package for solving physics-informed neural net training, physics-informed neural networks. We have hackathons, and we have nearly monthly or almost monthly seminars by leaders in the field. Short courses like Gian teaches also scientific machine learning, high performance research, computing, high performance computing. So I think that's it. So for the workshop, the plan is we're going to have these talks. These are 15-minute talks with 10-minute discussion. We're going to try to be very rigid following this schedule, because some people will be coming and going. And so I'm going to be keeping time and letting the speaker know when time is running out. And I'm going to get my watch, okay? No worries. And so we have an outstanding lineup of talks, and I'm really looking forward to this. We're gonna have a little break of 10 minutes, and then also at the end we're going to have a like an open forum for discussion about possible collaborations, funding, joint funding opportunities, and suggestions how to improve this effort here at Texas A&M. So this is my short introduction, and I thank everyone for coming and for volunteering to give a talk and for attending this workshop and contributing. So please contribute your insights and questions, and so this is basically what I wanted to say. So I'm gonna stop here sharing as soon as I'm able.